July 1944, Normandy hedgerow country. American P-47 Thunderbolts made their attack run over German panzer positions. The bombs tumbled from wings, small cylinders, 6 pounds each, clusters of 40. They looked insignificant. German tank commanders had seen bombs before. They stayed buttoned up, hatches sealed. Armor would protect them. The bombs hit. They did not explode. They burst open. Jellied gasoline sprayed across tank hulls. Stuck to metal. Ignited. The flames did not blow out. They did not wash away. They burned at 2,000 degrees Fahrenheit. They burned for 10 minutes. Tank commanders heard screaming from inside their own vehicles. Metal conducted heat. Interior temperatures exceeded survivable limits in seconds. Crews threw hatches open, abandoned vehicles, ran into open ground. American infantry cut them down. The tanks sat undamaged, armor intact, engines running. Crews dead or fled. The weapon was the M69 Napalm incendiary bomb. German after-action reports called it the paintbrush bomb. It painted tanks with fire that could not be extinguished. 1942. American air forces needed better incendiary weapons against vehicles and structures. Standard incendiary bombs used thermite or magnesium. They burned hot, yes. 3,000 degrees for thermite, but they burned in place. Drop thermite on a tank, it burned through the impact point. Miss by 2 feet, accomplished nothing. Magnesium bombs scattered burning fragments. Effective against flammable targets. Useless against armor. Both weapon types shared fatal flaw. They did not stick to targets. They fell, they bounced, they rolled away. Combat effectiveness against mobile targets approached 0. Gasoline burned well but too fast. Pour gasoline on metal, ignite it, flames consumed fuel in seconds. No sustained burning, no penetrating heat. The target survived. British forces experimented with thickened gasoline using rubber dissolved in fuel. Better adhesion, longer burn time. Results remained unsatisfactory. The mixture separated in storage. Rubber supply shortages limited production. Application required flamethrowers or ground placement. No viable air delivery method existed. American chemists at Harvard University approached the problem differently. Standard Oil Company had developed petroleum gels for industrial use. What if similar gels could thicken gasoline into sticky, slow-burning substance? Research team led by Louis Pfizer began experiments in early 1942. They tested dozens of thickening agents. Natural rubber worked, but supply constraints made it impractical. Synthetic alternatives performed inconsistently. The breakthrough came from combining aluminum salts with naphthenic and palmitic acids. The resulting compound, nicknamed napalm from its component names, gelled gasoline into thick, sticky substance. Mixed properly, napalm gasoline maintained consistency across temperature ranges. It stuck to vertical surfaces. It burned slowly, completely, at temperatures exceeding 1,800 degrees Fahrenheit. Most importantly, it could be loaded into bombs for air delivery. Development accelerated through 1943. Engineers at Standard Oil facilities in New Jersey refined the formula. Final composition stabilized at aluminum naphthenate and aluminum palmitate mixed with gasoline at 6% concentration. The gel remained stable for months in sealed containers. Temperature variations from -40 to +120 degrees Fahrenheit did not affect consistency. The mixture could be handled safely before ignition. Once lit, it burned with intensity that destroyed any material it contacted. Bomb design required innovation. Standard bomb casings were too heavy. Engineers developed thin sheet metal cylinders. The M69 weighed 6 pounds total, 2 pounds casing, 4 pounds napalm gel. Dimensions 14 inches long, 3 inches diameter. No explosive charge needed. Impact broke the thin casing. White phosphorus igniter, triggered by impact, ignited the dispersed napalm. Simple, cheap, effective. Larger versions followed. The M47 weighed 100 pounds. Metal tank filled with 70 pounds napalm gel. White phosphorus burster charge, scattered gel on impact. The M76 weighed 500 pounds for attacks on area targets. All versions shared core principle. Disperse sticky fire that burned long enough to destroy targets through sustained heat rather than explosive force. Production began in mid-1943. Standard Oil facilities at Bayway, New Jersey produced napalm gel. Bomb assembly occurred at multiple locations. Monthly production reached 1 million M69 bombs by early 1944. The small 6-pound bombs suited fighter-bomber loads perfectly. P-47 Thunderbolts carried 40 to 50 bombs per sortie. P-38 Lightnings carried similar loads. Even P-51 Mustangs, designed for escort duty, could carry napalm bomb clusters. The specifications proved revolutionary design. M69 weighed 6 pounds versus 100-pound conventional bombs. Fighter aircraft carried 8 times more incendiary bombs than explosive bombs by weight. Napalm gel burned at 2,000 degrees Fahrenheit, hot enough to weaken steel plate. Burn duration exceeded 10 minutes, far longer than any previous incendiary. The gel stuck to vertical metal surfaces, defying gravity. Wind did not blow it out. Water did not extinguish it. Nothing stopped the burning except complete fuel consumption. Compare that to German incendiary weapons. The Spring brand Granite. 41 Magnesium incendiary bomb, weighed 2 pounds, burned at 3,000 degrees, but consumed fuel in 90 seconds, too brief to penetrate metal through heat conduction. The Flam sea oil incendiary scattered burning liquid that washed away from sloped surfaces. Neither weapon achieved sustained heat. Transfer napalm delivered. Japanese forces had no equivalent weapon. Their incendiaries relied on magnesium or phosphorus, both quick burning. British incendiary bombs came closer, but still fell short. The 4-pound magnesium bomb burned hot but briefly. The 30-pound petroleum incendiary gel bomb used rubber-thickened fuel. Adequate adhesion, but lower burn temperature, approximately 1,400 degrees. Not hot enough to force tank crew evacuation through metal heat transfer. American napalm exceeded British capabilities by substantial margin. Before we see how this performed in combat, if you are enjoying the video so far, subscribing takes a second and supports the channel. June 1944. Normandy campaign provided first major combat test. 9th Air Force fighter bombers received napalm bomb loads. Target priority: German armor in hedgerow positions. The thick Norman hedgerows provided perfect cover for panzer units. Artillery struggled to achieve direct hits. Conventional bombs required precise placement. Napalm needed only proximity. July 17, 1944. Operation Goodwood. British and Canadian armor advanced toward Caen. German panzer units occupied defensive positions in Bourguebus Ridge area. American P-47s from 371st Fighter Group struck German tank concentrations. Each aircraft carried 40 M69 bombs. The attack saturated German positions. Napalm gel covered tanks, half-tracks, support vehicles. Everything burned. German reports from surviving tank commanders described impossible situation. Oberleutnant Hans Becker, commander of Panzer IV in Panzerlehr Division, wrote that American aircraft dropped fire that stuck like glue. His tank took no direct hits. Napalm splashed across engine deck and turret. Within 30 seconds, interior temperature made breathing difficult. Within 60 seconds, vision blurred from heat. The crew evacuated. American infantry reached the position hours later. Tank undamaged mechanically. Engine functional. Fuel and ammunition intact. Crew long gone. This pattern repeated across Normandy. German tank units learned quickly. When American fighter bombers appeared with small bomb clusters, crews evacuated immediately. Stay inside. Die from heat. Abandoned vehicle, risk infantry fire, but survive the flames. German tactical doctrine adapted. Panzer units dispersed more widely. Single vehicle positions instead of concentrated formations. Greater intervals between tanks reduced napalm saturation effectiveness. The weapon forced doctrinal change. August 1944. Falaise Pocket. German 7th Army attempted breakout. American and British forces encircled the pocket. Fighter bombers saturated roads with napalm. The results exceeded any previous air attack effectiveness. Vehicles caught in napalm strikes burned completely. Crews abandoned equipment. Traffic jammed as drivers fled burning vehicles. The entire German force cohesion collapsed. Post-battle assessment counted over 500 armored vehicles, abandoned undamaged except for burn marks. Crews evacuated rather than fight. September 1944. Aachen. Urban combat. American infantry faced German defenders in concrete buildings. Artillery proved ineffective. Building walls absorbed explosive force. Engineers requested napalm strikes. P-47s delivered M-4,700-pound bombs directly onto building roofs. Napalm gel poured through windows and collapsed roofs. Buildings did not explode. They burned from inside. Sustained heat made positions untenable. German defenders evacuated or died. Buildings fell to American forces without extensive explosive damage. Combat effectiveness studies quantified napalm impact. Fighter bomber sortie effectiveness increased 300% when carrying napalm versus conventional bombs. Abandoned enemy vehicle rates increased from 10% with high explosive to 40% with napalm. Infantry casualties assaulting burned positions dropped 60% compared to positions attacked with conventional weapons. Every measurement favored incendiary attack. German intelligence obtained unexploded M69 bombs for analysis. Chemical examination revealed composition. Manufacturing the weapon required materials Germany lacked. Aluminum salts in required purity. Stable fatty acids. Quality control in gel production. German industry could not replicate it. One captured document from December 1944 stated American incendiary weapons represented technology gap. German forces could not close. The assessment was accurate. Pacific theater employment differed. Japanese forces dug cave positions immune to conventional attack. Napalm proved ideal. Pour burning gel into cave mouths. Flames consumed oxygen. Heat propagated deep into tunnel systems. Defenders suffocated or burned. Flames survived longer than flamethrower fuel. One 6-pound bomb accomplished what 20 gallons of flamethrower fuel barely achieved. Marine and Army infantry relied heavily on napalm bomb support for Japanese fortified position reduction. Post-war analysis validated effectiveness. Strategic Bombing Survey examined napalm impact on German tank operations. Findings showed German panzer units modified tactics specifically to counter napalm threat. Vehicle spacing increased 30%. Concentrated attacks declined. Crew training emphasized rapid evacuation procedures. The weapon altered enemy behavior more than any other air-delivered incendiary. That alone proved its effectiveness. Post-war adoption spread universally. Every air force developed napalm weapons. Korean War saw massive use against Chinese forces. Vietnam War employment generated controversy, but proved tactical effectiveness remained unchanged. Modern incendiary weapons still use jellied petroleum derivatives. The principle established in 1943 remains valid. Sustained burning destroys what explosive force cannot. The numbers prove the innovation. 6-pound weapons carried in 40 bomb clusters. 2,000-degree burn temperature exceeding steel thermal limits. 10-minute burn duration forcing crew decisions under impossible time pressure. Adhesion to vertical surfaces defying defensive tactics. All developed in 18 months from initial concept to mass production. The M69 napalm bomb gave American Air Forces capability no other nation possessed. While German incendiaries burned briefly and fell away, napalm stuck and burned continuously. While British weapons required heavier delivery platforms, American fighters carried hundreds of incendiary bombs per squadron sortie. The jellied gasoline that looked like harmless paint drops melted German resistance through pure thermal physics. Tank crews who faced it once changed tactics forever. Those who faced it twice rarely got a third chance. The paintbrush bomb wrote the final word on armored vehicle vulnerability to sustained heat. That word was unstoppable.